One of the theorems that you'll need to know how to prove for A-level maths is Euclid's proof of infinite primes. So, Euclid's proof for infinite primes. Let me write that down. Theorem. There are many primes. I hope you remember what primes are, but if you don't, primes are numbers. So prime number p is a number such that the only whole numbers that divide p are 1 and p itself. So no other number divides p. Well, I guess you could say -1 divides p, but we don't, or perhaps minus p divides p, because you can find a number, for example, -1 times minus p would give you p, but we actually say that negative p is basically the same prime as p. Well, this is not the correct symbol to use, but essentially it's about the same prime, except that this is multiplied by a unit. So we don't actually count multiplication by a unit as a different prime. For example, you could say that 1 times p is different from p, right? And we just don't do that. That just it's not very useful to think about it in that way. So we say that negative p and p, well, not the same, but it's a multiplication by unit. So primes are only divisible by 1 and p, and we can say, if you want, positive numbers, and not 0, because 0 doesn't divide anything really, except maybe 0. Actually, I don't know about that. 0 doesn't divide anything. So how would you prove that there are infinitely many primes? In fact, because the definition for primes is, okay, what does it mean for there to be infinitely many primes? Well, that means that if you find a collection of primes, if you have a collection of primes, for example, here's a collection of primes, then you can always find another prime which is not in the collection, right? Perhaps using these numbers, you could find another one, or probably you wouldn't be able to use them to find another one, but there is a method known as the Sieve Method. So it's a sieve of Aristophanes, and I can't spell this name, so Aristophanes or something. And it says if you have all the primes, so P1, P2, P3, and so on, all the primes, so that all the primes actually less than some, in fact, all the primes less than some number n, right? You can use them to find the next prime. So you can, sorry, all the primes less than n, that means k is less than n, right? Then you can find the next prime. So if you have numbers 2 and 3, you can find the next prime. That's how you do it. You write down the numbers 1, 2, 3, 4, 5, and so on, okay? And you cross out all the multiples of 2. In fact, 1's a unit, so it can't be prime. And we'll cross out all the multiples of 2, okay? And then we cross out all the multiples of 3, and the first number that remains will be the next prime after these two, right? So that this works, so it's 5, and this always works as a method for finding primes. So what we need to show is that you can keep doing this, but it's actually not obvious to show how that there is always going to be a number like this. It's obviously you're welcome to try. I mean, it would be a good exercise to see if you can come up with anything that would do it. I mean, I'm not saying it's impossible, but I've never tried it myself. So, how do we prove that there are infinitely many primes? Well, we're going to use a proof technique known as proof by contradiction. And this is one of the proof techniques that you will need to know for A-levels, okay? And we will be doing another proof by contradiction that we're proving that square root of 2 is not rational. So we will talk more about this later. Don't worry if you don't understand this notation here. It just means that it can't be written as a fraction of whole numbers. So it can't be written as something like a half or three halves or something, or maybe even 6/4. It doesn't matter if it's in simplest form. It can't be written as a fraction. So how do we prove that there are infinitely many primes? I mean, I really should get to the point, shouldn't I? Well, suppose we have all the primes less than some number n, p1. Actually, suppose in fact, for proof by contradiction, suppose there is only finitely many primes, right? Only finitely many primes. So in fact, if there are only finitely many primes, we can write down all the primes in a list. So these are all the primes there are, okay? Suppose these are all the primes, okay? So first of all, we're saying that we suppose there are only finitely many primes. Excuse my spelling, that's not how you spell finitely, but you get the idea. So suppose there's only finitely many primes, right? And we need to show that this actually causes a problem. And if supposing there are finitely many primes causes a problem, that means that there are not finitely many primes, and therefore there are infinitely many primes, right? So how do we show that this causes a problem? Well, if these are all the primes there are, right, then we can make a number n here by multiplying all the numbers together. So p1 times p2 times pk. So multiplying all the numbers together. So if the set of primes was 2 and 3, n would be 6, okay? So multiplying all the numbers together. That means that every prime in this list divides n, right? But what happens when we add 1 to n? Well, for example, if 2 divides 4, and it does, then if we add 1 to 4, this no longer works. It no longer divides, 2 no longer divides, no longer divides what's on this side, because when you add 1, this will have a remainder of 1 after division, right? And that works no matter what prime it is. So if a prime divides n, then in fact it doesn't matter what number it is, as long as it's bigger than 1. Oh, very sorry about this. As long as it's bigger than 1, if you add 1 to what's on this side, then it's no longer divisible, because there will be a remainder of 1. Okay, so it's not divisible. So this is not divisible by any of the primes in this list. So we just found a number that's not divisible by any of the primes in the set that we made of all the primes, which is very strange because we said that if a number is not divisible by we showed that if in the last video we showed that if a number isn't divisible by all the primes less than its square root, then it's prime. And clearly it's divisible by all the primes less than itself now, right? Because we said that these were all the primes. So that, oh sorry, this should be not divisible. But that means that n plus 1 is prime. But n is clearly bigger than all the numbers in this list because we multiplied them to make n. So we found a prime that is not in this list, right? So this actually means there's a contradiction. We said one thing, right, which is there's only finitely many primes and that those are all in this list, right? But now we found a prime that's not in the list. So now that means that there is not finitely many primes. This means that there's not and therefore there's infinitely many primes. Well, I hope you enjoyed the video, and that's all about it from me.